record the try to record everything, but please remind me because I often forget. And I will put up the recording on YouTube, which you can have a look at. But I will not distribute the PPTs. Okay, so you will have to, at some point of time, just give me one more. Yeah, so at some point of time, you will have to I mean, it's best if you can note down what I'm teaching, the points that I'm covering, just as in class. Um, and if you want to go back, you'll have to refer to the YouTube channel. Now, first, let us have a look at the course. I have already sent you the course through the Google Classroom. And if you enrolled in the classroom, let's see. Your entire screen. Okay. So if you go into accept the invitation that I sent you, uh, you'll be able to enter into the Google Classroom. And your screen will, of course, be different from mine. And, okay, so some of you have already logged in. Let's see how many people have logged in. 29 students have logged in already, accepted the invitation. So what I'll be doing is, I'll be putting up the different announcements over here. As you can see, I have put up the syllabus, and I'll have a look at it again because this contains something which is very important for you. What books you will have to get. Now, this year, because of various reasons, mainly because you have started classes so late, we'll have to improvise to a lot of extent. Therefore, I normally start with Binmore's paper, Binmore's book, Mathematical Analysis. But this year, I'm going to start with the book by Hoy and others, Mathematics for Economics. In addition, you should also purchase this book, Chiang and Wainwright. So these two books, let me increase the size. So these two books are essential. Binmore you can drop for this year. Uh, Silverberg and Swain is another book that will help you. Sitzeta Hammond and Salmon and Bloom, we have kept it in reference, but you will require some sections, but the main part will be taught from Chiang and Wainwright, Hoy's book, and also to some extent Silverberg and Swain. Okay, so at the beginning, I would say that you acquire these two books. Both of them are available. You can get it, Chiang, you can get it in College Street, and both of them you can get it from Amazon or Flipkart. Uh, I will also show you a site. I hope you can see my screen. Hmm. Okay, so this is a site which is called the LibGen site, and if you search over here, you see there's a lot of books. Let us see. I think Hoy's book is available over here. Yeah, Hoy's book is available over here, third edition. So you can click on this book. You can click over here, and if you click on Get, you will get this Hoy's book. So LibGen is a site that you should use. Okay, this is a very good site for downloading books. So you should download Chiang and Wainwright from this site. I'm posting this so you'll get this site when you log in. Okay, but I would say that immediately download this, but you should purchase both the books because you'll require them not only just for your first year, but also for your up till your postgraduate level. Okay, so do try to purchase these books. Now, coming back to the course, you will see that we are supposed to start off with sets and subsets. Then we will go for functions and finally the concept of sequences. I think most of you have already covered sets and subsets. Am I right?
Yes, sir.
Yes,
I think
sir.
it's, I know it's covered in the ICC courses, Delhi board courses, but I think it's also covered in the HS courses now. So sets and subsets I will not cover. You can go through Hoy's book. It provides a fairly good introduction to sets. I don't think you'll find it difficult because it mainly refers to, uh, let's see, I'll open Hoy's book. So you can see what you have to cover. So this is sets and subsets. So what is a set? Then what is a proper subset? What is a subset? The concepts of Venn diagrams. What is union, intersection, null set? What is a complement? So I think you know what these are. So I'm not going to discuss this, but do go through them and also try answering the different questions over here. I'm going to start from numbers. Okay. So in today's class and in the next class, I'm going to discuss what numbers are, the concept of functions, and finally the concept of sequences, sequences and series. Okay. So let me go to the, okay. Okay. Now let us begin with the different types of numbers. I mean, this is fundamentals. Most of it you already know. So I'm not going to I'm going to go a little bit fast. And if you already know it, um, just hold on. Okay. So the first type of numbers is 1, 2, 3, 4, and it goes on like this. We call this Z plus. So we can say that Z plus is, if you want to count something, then we are going to use natural numbers. So if I ask you, how many books do you have to purchase? You'll have to say 2. You can't say minus 2. If I ask you, how much rupees do you get as pocket money? You'll again give a number uh, in this subset. So all numbers which we use for counting is called a natural number. Now, if you look at Z star, this has certain properties. If we take any two natural numbers, A and B, and if we sum them, will this also be the resultant sum? Let us say A plus B is equal to C. Okay. So does C also belong to the set Z star? If we take any two natural numbers, then will the product AB, will this product also belong to the Z star? Similarly for subtraction and division, A minus B. If A minus B is C, will C also be a natural number? A by B equal to C, let us say. Will C be a natural number? So what is your opinion? What is your take? Do natural numbers satisfy all these four properties?
Sir, can I say the answer?
Yeah, sure.
Sir,
But
I
can you
think
introduce yourself, please?
yes, sir. Yes, sir. Sir, I am Vaibhav Agarwal, and I am from Technanda Group Public School, Hooghly.
Okay.
And sir, I think the answer will be that for the addition and multiplication, it does satisfy, and for subtraction and division, I don't think it is necessarily right. Means A minus B may not, and A by B may not belong to Z plus.
Can you give an example?
So like for subtraction, if we do 1 minus 3, then the resultant will be minus 2, which will be an integer and not a natural number.
Okay, fine. And division?
So division, if we do 1 by 2, which it will
Yeah.
be 0.5, and that is also not a natural number. So that won't belong to natural numbers, sets of natural number.
Okay. Thank you. So I've deliberately made a mistake over here. These two are not satisfied. Natural numbers do not satisfy these two properties. Natural numbers satisfy only addition and multiplication. Okay. Now, if you come to see when you refer to subtraction, you said that subtraction doesn't satisfy. If I subtract A minus B, it need not fall within the set of natural numbers.
Yes, sir.
And an example was, let us say,
Sir,
5
I said
minus,
1.
yeah, let us say 2 minus 5, right? So what do we get? We get a number called minus. So just as we have 1, 2, 3 in the earlier set, now we can have minus 1 corresponding to each of these numbers, each of the natural numbers, we have a minus. And plus we have something which lies in between, the 0. So if we think of a number line, on one hand we have an infinite set of positive numbers. On the left hand side, we have an infinite series of negative numbers, and in between, we have 0. Now, the set of integers is closed. So that means, again, we are referring to the four properties, addition, multiplication. So Does it satisfy addition? If we take any two integers and we add them, a plus b, will c be an integer?
Yes, sir. Sir, may I introduce myself?
Yes, please.
Sir, I am Upanita Burman. I am from Garden High School. I believe, yes, sir, it will satisfy.
Yeah, addition. What about subtraction?
Yes, sir, that will also satisfy.
Okay. And the other two numbers, division,
So for division, it may not satisfy.
multiplication and division,
For multiplication, it will
it will
satisfy, but
satisfy.
for
And
division, it will not satisfy. May not
division, it will not. It may not satisfy.
satisfy.
I mean, obviously, if you divide 1 by 2, you'll get point.
Point
If you
five.
divide 2 by 1, you'll get 1. But what happens if you divide 1 by 2?
Yes.
So in that case, we come to the third type of numbers, rational numbers. Rational numbers are defined as the set Q. A and B both belong to the set of integers minus 0. So neither A nor B can be 0. Okay. So this part means B belongs to the set of integers excepting for 0. Z can be minus 3, minus 2, 1, 2, anything. It cannot be 0. A, however, can be 0. So we define a rational number as A by B. And when we are putting in this condition, it means we are ruling out division by 0. And the proof is, if we look at this, we can prove it. So I'll leave this to you as an exercise, and you should try it out at home after the class. If you can't do it, then we can discuss it later on. Okay. So we have seen that we started off with natural numbers, and then we proceeded to integers and rational numbers. Okay. So again, rational numbers, just like integers or natural numbers, extend in both directions. They comprise an infinite set. Now, if we look at the set of integers, the rational numbers will lie either on the integers or they may lie between two integers. Like over here, minus 9 by 4. This is lying between minus 3 and minus 2. Minus 5 by 4. This lies between minus 1 and minus 2. Similarly, on the positive side. So, if we take any two integers, there's an infinite number of points over here. And these rational numbers falls within these sets. Now, if I take any point over here, right? If I take, let us say, a point like this, where my mouse is, can I necessarily say that this is an rational number? I'm repeating the question. I have a set of points over here. Are all of them rational? Or can we have some irrational, can we have some points in between which are not rational?
Sir, I'm Oindrila Mukherjee and I'm from GD Billa Center for Education. I think we can have both rational and irrational numbers in between 0 and 1. Like root 2 is going to give us 1.414, which lies between, no, it lies between 1 and 2 though. But it's the
Yeah.
same. If we take numbers and then take the root of the numbers, then it can lie between 0 and 1.
Okay. Very good. So what we have is we started off with 1, 2, 3. These are the natural numbers. Then we added 0 and the minus values. We got the integers. Then we got the rational numbers, which lies between these numbers. But some of them, see, we have an infinite number of points. Not all of them indicate a rational number. We can also have irrational numbers, including what you have just said just now, that we can have, for instance, root 2. That can be a irrational number. So for instance, over here, I've taken two numbers, and let us say we want to find out the length of this 1.41, 0 to 1.41. Okay. So the length of this is given by, this is the Pythagoras theorem, the famous triangle and 90 degrees. So this will be 1 and this will be 1. So 1.41 is not given in the form of a by b. It is given in the form of uh, a square plus b square. So 1.41 cannot be expressed in the form a by b. Okay. So in general, however, if we consider any two rational numbers, let us say 1 and 2, then if we have a number like this, 1 plus 2 minus 1 divided by c, then c must be a rational number which lies between 1 and 2. Okay. So depending on what the value of c, we can have different points between 1 and 2. But not, as I've said, not all the points, only some of the points. So this can be generalized. We can write this as a plus b minus a by c. So a can be minus 3, b can be, let us say, 2. And depending on the value of c, we will have a rational number which is lying between these 2 points, minus 3 and plus 2. Okay. So is it clear, or does anyone have any questions? Okay. Now, if you combine the set of rational and irrational numbers, the resultant set is called real numbers. Now, real numbers satisfy certain properties which are very easy to understand. Closure, for instance, that if a and b are both real numbers, then the summation will also belong to the set of real numbers. And this holds for product also. A into b, the product is also a real number. Therefore, R, or the set of real numbers, is closed under addition and multiplication. Then is the commutative law. So for all A and B which belongs to R, we satisfy the commutative law. Do you know what the commutative law is? Can you guess? Someone guess? You should know it, in fact.
So can I try?
Sure.
So
You are?
if Upanita Burman.
Okay, okay.
So if A plus B is equal to B plus A, if I can say that way.
Let's see whether you are right or wrong. Ah, you have become a crorepati. Similarly, for multiplication. So the order, whether A comes first or A comes second, is not really important for addition or multiplication. Associative law, here again it's the same. we are working with three numbers, and as you can see, the order of addition or the order of multiplication is not really important. In this case, we are adding B and C, then we are adding A. Here we are adding A and B, then we are adding C to the sum. In both cases, we will get the same number. Here, we are first taking the product of B into C and multiplying this by A. Here, AB is multiplied by C. In both cases, we get the same result. Distributive law, sorry, the C is capital. In distributive law, we are basically, what we are saying is that B plus C, this is the, you can say we are combining the product and addition, the multiplication and addition rules. So here we are adding B plus C and then multiplying by A. Here we are doing the multiplication first and then we are doing the summation. So the order of operations, whether we do the addition first and then the multiplication, is the same as whether we multiply first and then we add. Zero. No one loves zero, do we? If we get it in the exams, we don't like it. Unless you are very clever and you can add, you can write 10 before it. So zero is defined, sorry, there's a typo over here. The element zero belongs to the set of real numbers because it's an integer. It has the property that, uh, sorry, I'll have to correct this. This is a plus 0 is equal to a. Similarly for product, a0, a into 0 is equal to a. 1 is defined such that 1 into a is equal to a. Finally, negation, the last two properties, negation. So if we are uh, taking the negative of a real number and we sum up the real number and its negation is going to be 0. 5 minus 5, 3 plus 3. Next is reciprocal. We take a number and we find out its reciprocal, 1 by a. If we multiply the number by its reciprocal, it's going to result in 1. Now note one thing over here. Here we were taking, in case of negation, we were taking all the real numbers, including 0, right? If we take 0 and what is this negation? Minus 0. So 0 and minus 0 is equal to 0. But in case of reciprocal, we are not taking 0 because as we have shown before, 1 by 0 is not possible, is not allowed. Okay, so I'm going to ask you to show that uh, for any a and b which belongs to the real number, if a plus b is equal to 0, then b must be equal to minus a. So I'm going to stop presenting and please try to work it out yourself. And you can present it before the class.
So can I answer?
You'll have to present. Can you present and show it to us?
Yes, like the working out of the problem.
Yeah,
Do you want me?
yeah,
Okay.
yeah. You can write it out in Word or PPT. Word is better, I think.
Okay, sir, I'll do that right now.
Yeah.
So can I show?
Yes, please. Where are you from? You're Rajashree Khan, right?
Yes, sir. I'm from Yamitpur Asansol from AGZ School, Sodhpur.
Asansol.
Yes, sir.
Okay.
So can I show you the copy?
Yeah, yeah, please.
So, so here it is. That if A is equal to -1 and B equal to +1,
A is equal to.
-1.
No, this is what you have done is it's specific.
Yes,
You
sir.
have to show the general result. Suppose I take a different set of numbers. Will the same result hold?
So can I show you my copy?
Sure.
So, sir, just a few minutes back, you taught us by the property of negation. We
Yeah.
learned that a plus minus a is equal to 0. And we're supposing here that a plus b equal to 0. So we can conclude from that that b is equal to minus a.
Okay. Thank you. Where are you
Thank you.
from?
Sir, I'm from Uttarpara, Hooghly. I completed my schooling from Pulse of God.
Uttarpara.
Yes, sir.
Varma Apartments. Is it still
Yes,
there?
yes, yes. Yes, it's still there, but I'm not a part of it though. It's in front of the Ganga, but I'm not a part of it.
Then you're a minority. I think Varma Apartment
Exactly,
is the entire of Uttar, almost the entire.
exactly.
I've
It's
been
a
there.
huge buzz here. It's a huge buzz here.
Yeah. Okay. Um, okay. Actually, what you can do over here is
Hello,
you
sir.
have, yes,
Oh, sorry, I didn't mean to interrupt you, but I was just saying that in order to make the proof more generalized, we can
yes,
just take a plus b is equal to 0, which is given, and then we can subtract a from
yes,
add the negation of a to both sides,
yes,
which will give us b is equal to minus a.
yes.
Yes, sir. Thank you. I'm Kritika Ghosh this side from Kolkata.
Yeah. Okay. So we have a plus b equal to 0. So what we're doing is we are adding a minus a. So we'll get minus a and a cancels out, b is equal to minus a.
Yes, sir.
Okay, so this is the proof. Now, sorry. So this is the proof. We have a plus b equal to 0, and we simply add minus a to both sides. So we know that a and minus a is equal to 0. So this part left hand side becomes sorry, this should be B. B is remaining, and we have minus A over here on the right hand side. Okay. Okay. So next we come to the order properties of um, the set of real numbers. So here you can see that there's a subscript. We have two pluses. This means that we are taking only those real numbers which are strictly positive. Strictly positive means they lie on the right hand side of the number line, and second, we don't take 0. So we take 1, 2, 3, so, and plus also the 1.5, 1.6, so on. The real numbers, rational and irrational numbers. So this set, strictly positive real numbers, is both closed under addition and multiplication. Secondly, if we take any number, then one of the following has to be true. So either A is strictly positive, or A is equal to 0, or if you take the minus of A, then this becomes strictly positive. Okay, this is intuitively obvious. In this case, we see that A is not part of R plus plus. But in these two cases, here also we can say that A is not part of R plus plus. So only in this case, A is part of uh, sorry, A is part of R plus plus. Okay, but in general, A belongs to the set of real numbers. Okay. Next is we take the set of strictly positive real numbers and we add 0. We will get R plus. So it is the set of non-negative real numbers. So minus 1, minus 2, minus 1.5, or irrational numbers which are negative, these are dropped. So if you are given any two numbers, A and B, which belongs to the set of real numbers, then the following properties will hold. Just have a look at them and see if you have any problem in understanding any of the properties. Yes. Okay, we had a late entry. Okay, so is it clear? Are these four properties clear, or
Yes,
does
sir.
anyone have any problem? Okay. Now, based on them, we can develop a theorem that if we have two numbers, two real numbers, A and B, completeness means that one of the following is true. Either A is greater than B, or A equal to B, or A is less than B. See, this part is very important because later on when MD will discuss consumer theory, the theory of indifference curves, you are going to use these axioms. You'll have to understand the definition of completeness, transitivity. In fact, transitivity is very important, and you will require this later on, even in your postgraduate level. So completeness, what we are basically saying over here is that if we take any two numbers, we can rank them. We can see which is higher, which is greater. And obviously there can be three possibilities. Either A is greater or B is greater. And the third possibility is they are equal. Right. The second property is transitivity. Transitivity means that suppose we have A greater than B and B greater than C, then A will be greater than C. Okay. Similarly, if instead of taking a strictly greater than, we take a strictly less than, then this is also a transitive relation. Now, if we over here, what we are doing is basically is we have taken three numbers, right? Three numbers in three real numbers, A, B, and C. If we extend this, so we are taking, let us say, x1, x2, x3, x4, ad in infinitum. So what we are saying is x1 is greater than x2, which is greater than x3, which is greater than x4, and so on. What is the relation between x1 and xn? So
So
instead,
x1 is greater than xn.
what do we call this property?
Transitivity.
No, this is transitivity, but if we extend this to a larger number, transitivity refers to when we are comparing between three numbers. If we compare between a huge set of numbers,
Completeness.
completeness is you're simply ranking them.
So can I say?
Yes,
Sir, I'm Anushka. It's increasing.
no.
So
Achha,
is
by
it
the way, just
the
one sec, please. Why is it not completeness? In
Uh,
completeness, see,
because it has to be equal
x1,
also.
see, completeness allows for x1 and xn to be equal. It also allows xn to be larger than x1. That is why it's not a case of completeness.
So can you repeat?
Yeah, in case of completeness. See, what I was saying is,
Yes, sir.
see, what I'm arguing is, I'll take this case because it's easier to write. Okay, so what I'm saying is that suppose I have a relation like this. Okay, then this implies that x1 will be greater than xn, right? Now, what is this property called? So one person said it was completeness. See, it's not completeness because what we are doing is we are basically extending the property of transitivity. In case of completeness, either of the three possibilities can hold, right? But here we have only one type of this. So it's not really completeness. Let me give an counter example. Okay. Suppose we had this. Suppose we have this. What do we call this? Does this form, uh, if you think of it conceptually, does it form and give you, can you think of a geometric image?
Sir?
Does this line, which I've shaded over here, this red part, does it suggest any geometric shape to your mind?
Sir, may I answer?
Sure, sure.
Sir, I am Prithviraj বিশ্বাস, sir. Is it monotonicity?
No. What are the different ways? I mean, some of you have maybe going to schools which are very close, but okay, I'll give you a hint. Uh, what are the two most important inventions of
Issa,
man?
are you talking about mirror and light and reflection?
No, I'm asking. We will come to reflection later on. I'm simply asking you that what are the two greatest inventions by mankind?
Wheel and fire.
Yeah.
So does this show a wheel? Well, like it's a circular thing where x1 is greater than xn, but at the end xn is even greater than x1.
Yeah.
So it forms a circle kind of.
It forms a cycle. It forms a circle, or what we can also call it, we have a cycle, right? So this is
Yes.
called cyclicity. Okay, and here we don't have cyclicity. This is called acyclicity. Okay, so if you have three numbers, it is transitive. Let me bring this at the top. So here, the greater than or greater than equal to, both the relations will give you a transitive relation. But if you extend transitivity to more than three numbers, we refer to this as acyclicity. Uh, in fact, sorry, I've made a slight mistake. Uh, sorry, this is what we transitivity implies that xn is not equal to x1, which will give us the relation xn, right? So we refer to this as acyclicity and this as cyclicity. Okay. So obviously, if it is acyclic, we are going to have this type of relation. X1 will be greater than Xn. Now, you refer to a mirror image. Here, we have something which is similar to that, a mirror image. So if A is greater than equal to A, and finally equal to, if A is greater than equal to B and B is greater than equal to A, then A and B must be equal. Now see over here, we are using the symbol greater than equal to. Over here, we have used the symbol or relation greater than. Okay. Now let us think of a relation P. P basically means preferred to. Okay. So that means if I give you two options, A and B, A, P, B means A is preferred to B. So A, P, B means so. Now suppose you have uh, three bundles, three options, A, B, and C. Okay. Will it be transitive? Will it satisfy the property of transitivity?
So can you repeat the question once, please?
Okay. So you have three bundles, A, B, and C. Okay. So suppose, so will this relation P be transitive?
Yes, sir.
Yes, sir.
Yes,
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 sir.
sir.
Well, before that, we must first ensure that we have this completeness. So for any two options, if we take any two options, we can rank them, right? What does A prefer to B means? A is a better bundle, right? What is
Yes, sir.
B preferred to A means? B is a better bundle. Can we have, is it possible to have both? A preferred to B and B preferred to A?
No, sir.
Yes, but if they're identical bundles,
If they are identical bundles, will you prefer A to B?
we'll be indifferent to both of them.
Yes.
We will be indifferent to both of them.
Yes, sir.
Okay. Uh, let us assume that we have you're given some options. Okay. And you can rank the options either using P or using I. Okay. So either you will have A preferred to B or B preferred to A, or you have AI, B. You're indifferent between A and B. Let's think of possible combinations. Okay. What is the relation between A and C?
A is preferred to C.
3 is preferred to C.
Yeah, A is preferred to C. Suppose you have sorry, now
So indifferent.
why not preferred?
So because I don't think it's given anywhere.
So we can't comment on this because A might be higher than B or B might be higher than A because both are in retrospective to C.
So here we can't really see what is the relation between A and B.
So
Yeah, yeah. Is this clear?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, so if any of you have any problem, please ask. Okay. Now the next point that I want to stress on, a very small point, but it can create a lot of problems. That is, when we are measuring economic variables, we measure them in different units. For instance, labor used. Uh, we can measure in terms of labor days. How many days of work have you put in? How many hours of work have you put in? Uh, how many kilograms of, or rather, how many vials of Covaxin have you purchased? What is the cost in rupee terms? Okay. So different variables are measured in different units and we call them dimensions. Now, when we are adding units, we have to be very careful if we that we should not add units which are dissimilar. So, for instance, if we are adding labor to capital, it is not possible because labor is in man days and capital is number of machineries. We cannot say that I have worked for 5 hours plus I have used a computer. So 5 plus 1 is equal to 6. This is not possible. In that case, what we have to do is convert them into a similar unit. Or what we can do is we can convert them into pure numbers which do not have a dimension. For instance, what is the rate of interest? Interest by principal. Interest is measured in rupees, principal is measured in rupees. So the rupees cancels out in the numerator and denominator. So in similar ways, if we can find out what is the rate of interest, what is the rate of profit, we can add these two. But we cannot add uh, variables which are measured in different units. Finally, we come to something which I rather used to like. During our exams, we used to be given graph sheets, graph papers, and I really liked using the graph papers. What we have over here is a two dimension. So we have if you look at this, this is a number line. And any point over here is a real number. We have over here a set of natural numbers 1, 2, 3, 4, but we also have 0, we have minus ones, and in between we have the rational and irrational numbers. So this is one number line, this is another. Using these two number lines, see, so far what we have done is we have taken one number line and we have just identified one point over there, x2, x1, x0. If we take this as a number line, y0, 0, y1, these are points on the number line. Now, when we take two different number lines, instead of we still get one point. But now, this is described as a combination. We have to define this point as a combination of x2. How do we get x2? Using this number line. How do we get y2? Using this number line. So x2 and y2 is given by this point. This is x0, y0. This is x1, y1. You can see over here, both x0 and y0 are natural numbers, or at least they are strictly increasing numbers, r plus plus. Here, x belongs to r plus plus, but y1 is r minus, minus minus. Here, both of them, x and y, both are r minus minus strictly negative. X2 is also strictly negative, y2 is also strictly negative. Okay, so we are taking two number lines. Now, obviously, I can't draw it, but you know that we can also increase the dimensions, coordinates. We can expand it to R3, r to the power of 3. We take 3 number lines. In that case, you will have a number line which comes out from here and which comes out of the computer. We can go on adding the dimensions r3, r4, r5, in which case a point is defined as, if we take r3, we have to define it in terms of x, y, and z. If we take r4, a, b, c, d in this manner. Now, the concept of intervals is something that is also going to be very useful to us. Suppose we have a and b, which belongs to the set of real numbers, and for convenience, we assume that b is greater than a. We can think of uh, 4 types of intervals. Okay, let's go back to this. I'll require this. Suppose this is one number x2 and this is x0. Ignore the y number. Okay, we are just taking just one uh, number line, and we have taken 2 points over here, x0 and x2. So we have different points. We have a lot of points in between x0 and x2. Okay. Now, our set can comprise of, if you want to define a set using boundaries, x2 and x0 are boundaries, we can define it in 4 ways. One is we can include both x0 and x2 within the set. So the boundaries are included within the set. In that case, we call it a closed interval. And you can see it is denoted by square brackets. Clear? So square bracket means that A, the lower boundary, and B, the upper boundary, are both within the set. And all the real numbers between A and B are within this set. What is the other extreme? We don't include A and B within the set at all. You can see instead of the square bracket, we have the first and second bracket. Instead of the greater than equal to, we have strictly equal to, strictly greater than, strictly less than. Okay. This is called an open boundary. So open boundary, closed boundary, these are the two extremes. And in between we have two hybrids, which are called half open or semi-open, or semi-closed or semi-half closed. Here, what we have is that A is included within the set. The lower boundary is included within the set, but B is not included within the set. So here we have greater than equal to, but here we have strictly less than. Okay, so the lower boundary is closed. We have square brackets. The upper boundary B is not included. So we have the curved bracket, first bracket. Here, the half open or semi-open interval is bounded from below, strictly bounded from below, but weakly bounded from above. In this case, it's exactly the opposite. E is not included. The lower boundary is not included within the set. It is only B that is included within the set. Okay. So in both cases, we can see that there's a boundary. Okay. We cannot go beyond A and B. Whether we can touch A and B or not, that depends on whether it is closed or open. But let us look at this, infinity. This is closed, so x can equal to A, then x goes on. X can be equal to minus 1, plus 1, plus 3, plus 4, 4.5, 4.9, 7.2, it just goes on. There's no end or there's no boundary to x, to the maximum value that x can assume. So this is unbounded from above. Can you define an unbounded from below? How do we write an unbounded from below?
So we can take minus infinity.
Negative infinity.
What will be the brackets?
So
Sir,
no open bracket before negative infinity and close bracket before after a.
Yeah. And what is the third possibility? In case
Negative
of
infinity to
infinity
Negative
to
positive
infinity
positive
to
infinity.
infinity.
positive infinity.
okay, so we have the first brackets, minus infinity and plus infinity. Next, we come to the concept of convexity. Let me give the easy definition of convexity. Suppose we have a curve like this. Now, if we take any 2 points on the curve, right, and we connect them, see the points on this line is below the curve. This is called, sorry, just a minute. Acha. Okay. This is better. Here we have, if we connect any 2 points on the curve, then a point on the line is above the curve. The entire line is above this curve. Okay. So we define convexity and concavity in terms of using this diagram. Now, can you tell me what is convex and what is concave? Which of them is concave?
So the second one is concave.
You're saying?
Yes, concave. This one is convex.
Sorry. Convex. Okay. Acha. Mm, sorry, actually, I didn't want to discuss concavity over here. Mm, let's focus on convexity. Okay. Mm, okay. When we are taking a convex combination, okay, we have 2 points. Let us say x1 and x2, and both of them belong to the set of real numbers. Sorry. Okay, so that means x1 is a point like this. X2 is another point in a two-dimension space. And we draw a line connecting x1 and x2. So a combination is, suppose we have for any insert, then for any lambda which belongs to the set, the closed set 0 and 1. That means, can lambda be equal to 0? What does it imply?
Yes.
Yes,
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 sir.
it's
Yes,
fine.
sir.
Yes.
Yes,
both
sir.
are inclusive.
Both are inclusive. But if I do it like this, lambda
Only one
cannot
is
Then
be.
the
Excluding
included.
then
zero.
zero is
Does
not
not belong to
included.
Points.
0 but belongs to 1.
Yeah. And obviously lambda can be any point. So that means lambda can be 0.5, 0.3, 0.7 and so on. So for any lambda, we have the relation x is equal to okay. So for a two-dimension space, we write it like this. And okay, so if we take any 2 points in a two-dimension space, let's go to the concavity. I don't need this. Sorry, I'll just remove this. Mm. So I've got 1 point over here. Sorry, this will be easier. Okay, so I've taken 2 points, and a convex combination of the 2 points is simply I draw a line between them, and any of these points is defined as a convex combination of, let us say this is x1 and this is x2. So the point x, if x is a convex combination, we say x lies on this line.
So, so this basically means that the coefficients have to be always be non-negative, right?
Yeah, by coefficient you mean lambda,
Yes,
or do you
yes.
mean a? Because x1 can be non-negative. I can,
Okay, okay. Oh, right, right, right. Yes. But lambda will always be positive.
yeah, lambda is not only positive, it will be from 0 to 1.
To one.
If
Yeah.
it is 0, then x will be equal to x1,
Yes.
right? If
Yes.
lambda
Thank
is,
you.
yeah. So depending on what the value of lambda is, 0 and 1, x will be either equal to x1 or it will be equal to x2. And if lambda is a fraction, it's going to lie within the
Within.
set.
Okay.
Now, look at this. Better still, let me draw this. Insert. Yeah, look at this. If I can take points within this um, figure, right? If I take any 2 points within the figure and connect them by a line, what will happen? It will remain, it will be part of the set, right? So this when I really miss the blackboard. Let me pull it a bit closer. Right. So you can see I've taken 2 points within this circle. Let me make it a circle. And if I connect them, all the points on this line, all convex combinations of x1 and x2 will also lie within this set. If I take let us say, a rectangle, right? Again, you can see that if I take any 2 points within this rectangle and connect them by a line, the points on this line will lie within the rectangle. Okay. Now look over here. Look at this figure. In this, what I said about this, is it satisfied over here? If I take any 2 points, will it necessarily lie within the set? Let me go back. So I have a set like this. Look at it. So suppose this is the set. Okay. The point within the smaller circle, it is outside the set. I can't color it. I'm sorry, but I'll just use this. Okay. So outside this set, this part, that is not part of the set. Within this smaller circle, this is also not within the set. Only this part within the two circles. That is this R set. If I take like this, right? All the points on this line, all the convex combinations are within the set.
Yes, sir.
If I take this, again, yes. But if I take this,
No, sir.
these points are
Yes.
within the set, these points are within the set, but not these, right? So in this case, for instance, what happens? If I take any 2 points, will the convex combination also lie within the set?
No, sir.
No, sir.
Yeah. If I take a point like a line like this, it will lie within the set. But here, if I
It
take a
won't.
point like this, a point like this, or even from here to here, we have some points on the convex combinations which are outside the gray areas. Okay.
Yes.
So if you have a set, by set I mean these geometric sets. So you have a two-dimension graph and you take a subset of points, okay, which forms a set. That forms your set. Whether it is convex or not can be found very easily. You take any 2 points on the set and connect them by a line. All points on the line must be within the set. So this ellipse, this circle, this triangle, this rectangle, In fact, even this line also, all of them are examples of what we call strictly convex sets. But if you look at the right hand side, see, this is a curve. If we connect them, points over here are not
Not on
on
the.
the within the set. Over here, all these 5 examples, these are not convex sets. Okay, so you know what is a strictly, I mean, in physics, you know what is convexity and concavity, but now we are discussing something called the convex set. So I hope all of you understand what is a convex set,
Yes,
right?
sir.
Yes,
Okay.
sir.
Yes, sir. Yes, sir.
So I think I'll end at this point. And if you have any query about anything, about the lessons or any other issue, I'll be glad to answer it.
Sir, can you please show once again how we can download the book from LibGen?
Okay, I think it is better if I stop recording.